Assalamualaikum warahmatullahi wabarakatuh and good day. Now we look at example 6.14. Let y1 and y2 be independent exponential random variable, both with means beta greater than 0. Okay, so here you can see you have y1, y2. This is an independent exponential random variable. And then the question asks you, find the density function of u equal with y1 over y2 plus u equal with y1 over y1 plus y2. So first, you must know the density function for y1 and y2. So since mentioned y1, y2 is an exponential random variable, this one, alright. So this is your density function for y1 and y2. Okay, so you can see that the parameter here is beta. Okay, and then y1 is greater than 0, y2 also greater than 0. Now you need to find the joint density function of y1 and y2. So since it's independent, so you just can multiply the density function. So when you multiply the density function, you can see that the power of exponent you can add. So when you add, it becomes exponent negative y1 plus y2 over beta. And then here you get 1 over beta square because of this multiply. 1 over beta times 1 over beta, you get 1 over beta square. And then here you have two random variable, which is y1 and y2. Both are greater than 0. Okay, so you can do this because y1 and y2 are independent. So in this case, the joint density function is greater than 0. Okay, you can see from here. For all value of y1 and y2 because of this limit. Okay, and then here we are interested in the function u1, okay, equal with y1 over y1 plus y2. Okay, actually we have this one. Okay, we have this one. Okay, but here if we consider the function u1 is equal with y1 over y1 plus y2, then there are obviously many values of y1 and y2 that will give the same value for u1. So let us define u1 equal to this one. So this is the first function of h1. Okay, and then you let u2 equal to y1 plus y2. Okay, even in the question didn't given, okay, but you can see that you can do that. So we can do that because okay, we have we can let lah. So easier for us to solve this question. Okay, so we let u2 equal to y1 plus y2, which is this one. Okay, so this one become your second function, okay, of h for y1 and y2. So this choice of u2, okay, yield a convenient inverse transformation. So that's why how to choose, you must be creative, okay. When you choose, make sure that it's easier for you to differentiate or to transform, okay. So in this case, when we substitute this one equal to u2, okay, so you can substitute here, isn't it? So that's why we can have here, let's say from here actually you will get u1. Okay, u1 equal to y1 over u2, and then you want to make y1 as a like this. So that's why you times with this one, you get u1 times u2. So this is the inverse function of u1 u2. And then the second one, this one, you need u2. So that's when you have y1 plus y2 equal to u2. So u2 is equal with u2 minus u1. So what is u1? u1 is y1 is u1 times u2. So this one actually you get here, actually from here you get u2 minus u1 u2. So that's why when you simplify or factorize this one, you get u2 1 minus u1. You get this one. Okay, so this is the second function for u1 and u2. Okay, so you can see the step is similar. You have first this density function for y1, y2, and then you find the density, the joint density function for y1 and y2, and usually it's independent. So when it's independent, it's easier for you to multiply, okay. And then you look the interested function. So here we interested in u1, okay. If you have 2, then it's 2 lah. If you have 1, you have 1 here, but then you need to let the u2 here. Okay, and then you need to find the inverse function. Okay, here is called inverse function, and where we do the transformation. Okay, so after this, you need to find the Jacobian of this transformation. Okay, so you can see that the first function, you differentiate with respect to u1, you get u2. Okay, and then you have the first function, you differentiate with respect to u2, you get u1. Okay, you differentiate partially. Okay, and then for the second function, this one, you differentiate with respect to u1, you get negative u2. Okay, actually from here you can see lah. Okay, this one, you differentiate this one, you get negative u2. Okay, and then this one, if you differentiate with respect to u2, you get 1 minus u1. Okay, so here then you find the determinant u2 times 1 minus u1 minus u1 times negative u2. So finally you get u2. Alright, and then the joint density function for u1 and u2 can be found by, you have this inverse density function times with Jacobian. Okay, again here you must find the limit as well. Alright, so when you rearrange, you multiply. So you can see that the density function for u1, uy, the joint density function for u1, u1 is greater than 0. If u1 and u2 are such that you have u1, u2 greater than 0 and this one greater than 0. And here, important, okay, you have u1, u2 greater than 0. So this one actually, if you substitute if you simplify this one, you get this one. Alright, and then you can bring to the left and to the right. It's implied, okay? u1, u2 is between 0 and u2, and then u1 is between 0 and 1. Alright, so for the limits ni, I'll show you, okay, how you get. So basically this one, from this one, okay, from this one, you just multiply back, you get this one, isn't it? And then you look here, u1 times u2 is greater than 0. So from here, actually, you can have that. Okay, actually you have u2 minus u1, u2, isn't it? So this one you bring to the left, and then you know this value is greater than 0. So that's why you have u1, u2, alright, and then here is u2 lah. Okay, because this one you bring to the left, and then you know this function, or I mean the u1 times u2 is greater than 0, so you can do this. Alright, so in order for you to get u1, from here you bring u2 to the right. Okay, so from here you bring u2 to the right, so you will get u1 greater than 0, and here is u2 over u2 is equal with 1. So that's why you have this one. Okay, alright, so if u1 is between 0 and 1, then u2 times 1 minus u1 is greater than 0, so it implies that u2 is greater than 0 as well. Okay, so therefore, the region of support for the joint density function of u1, u2 is between this one. Okay, u1 is between 0 and 1, and then u2 is greater than 0. And the density and the joint density of u1, u2 is given by this one. So remember the formula in order for you to get the joint density function of u1, u2 is given like this. This one. Okay. So this is when you substitute, you confirm the limit, then you will have this one. And then another important here, using theorem 5.5, it is easily seen that u1 and u2 are independent. Okay, because the marginal density of u1, u2 can be obtained by integrate the joint density derived earlier. So that's mean if you want to find the marginal density function for u1, u2, you can use theorem 5.5 by using this joint density function. Okay, because we know it's independent. All right, and in exercise 6.63, okay, you will show that u1 is uniformly distributed over 0, 1, and that u2 has a gamma density with parameters alpha equal to 2 and beta. So this one, after you find the marginal density function for u1 and u2, you can see that u1 follow uniform distribution over 0, 1, and then u2 follows gamma density. Okay, so as a homework, I want you to try this exercise 6.63 and then look, do you understand or not? Okay, so I think that's all for this video. So try do more exercise. Okay, the step is still similar. Okay, but the difference is in term of question lah. Alright, so thank you class.